let's talk about future changes. And again, this is something that is going to affect everyone in this room. So we are going to cover today what the Earth is going to be like by 2100. And that's, I think, a really interesting thing, and it should be of interest to everybody. And we're going to look at the range of possibilities. Okay? We're going to see sort of the best case scenario. We're going to look at the worst case scenario. We're going to look at some of the sort of the factors that mean that there is this uncertainty. Okay? So as a reminder, quiz 10, if you need one last quiz score, and it's a good chance for you to practice answering some questions about the stuff that we've done this week. It's available as normal from 2 p.m. today till 1 p.m. Monday. Okay? So take a chance to do that. And if you do have a couple of minutes, please do fill out the evaluation. I would really value your comments. Thank you. Okay, so we did this on Wednesday. We talked about how our climate is changing today, the fact that we can see changes. There's no arguing about this. We can see changes in the Earth's temperature, in the atmosphere, in the oceans. We can see that the cryosphere, the ice part of the Earth system, is melting. We can see acidification of our oceans. We can see changes in precipitation patterns. We are seeing change. And some of that change, especially, is really unprecedented on at least decades and possibly thousands of year timescales. And so something is going on. And really, if we look at all of the factors that control our climate, ranging from things like solar variability through land use, aerosols, into things like greenhouse gases, then really we can see that the greenhouse gases are having a huge influence on actually warming us up. So remember way back now in the class, we talked about the solar constant, this sort of 1,370 or whatever else watts per meter squared that arrives at the top of our atmosphere. Some of that gets reflected back, but a certain amount is absorbed at the Earth's surface. What we're effectively doing by adding greenhouse gases is adding maybe 2.5 watts per meter square to that sort of value that we had before. And that's happening every day, every minute. We're absorbing that extra amount of energy, and so we're getting warmer. And as we're accelerating the increase in the amount of greenhouse gases in the atmosphere, we're accelerating the amount of extra energy that we're trapping. There's really no fundamental sort of argument about that. If we have more greenhouse gases, we're going to trap more energy. And so now we're going to look at some of the future changes that might result from that. And to do that, we can't just sort of necessarily do a couple of quick calculations on a piece of paper. Because the climate system is such a complex interacting system, we have developed pretty complicated climate models. And these are some of the things that they incorporate. Oh, my iClicker thing is all over the place. It includes things like the land distribution. It includes our atmosphere and ocean, and not just the fact that they're there, but also you can see that we have these different boxes. Okay, so each of these boxes going up represents a different level in the atmosphere. Then we have our ocean, we have ice cover, we have things like the biosphere, and that's also dynamic. So as we see changes in temperature and precipitation, the biosphere will respond to that within our climate models. We have things like the water and energy. I mean, you saw how much sort of latent heat energy is so important for atmospheric circulation. We have to build these things in, as well as things like the carbon, the nitrogen cycle. And there are all these sort of very complicated sets of physics and chemical equations that basically govern the flow of energy and material across each of those boundaries between those different boxes. So it's obviously going to take an enormous amount of computing power, and that's really where the past couple of decades have helped us out, because we've got better and better and better sort of computing power, and we also just sort of understand this system a lot more. And so climate models have come a long way. So those of you that are into computer games, which I know is most people, if we went back 10, 12, 15, 20 years, then that first annual report, it looks more like those sort of blocky, like Donkey Kong type early video games, whereas now we've got really much more advanced. And this fourth annual report, this is sort of what our climate models would look like. So you can see how the resolution of those climate models is getting better and better as we're getting sort of more able to represent the climate systems. And we still have a long way to go. There are still interesting things that we can't quite get right in our climate models. But overall, they're a really pretty good representation of the climate system. I think remarkably good, given how complicated it all is. And now we're doing things like trying to build in things like the isotopes, those carbon isotopes we talked about, to help us pin down even more carefully what's going on. And so we have these wonderful climate models, but we can't just sort of run them without at least putting in some information about what the future will be like. And really, this is where a lot of the uncertainty comes in. If you could tell us tomorrow exactly how much carbon we're going to be emitting, what our population is going to be, and where our energy is going to come from for the next 100 years, we could give you a much better answer about what climate is going to do. The uncertainty, a lot of the uncertainty when we say, well, temperatures could be between this and this, say, so 1 degree or 6 degrees Celsius increase by 2100, a lot of that uncertainty is to do with us, is to do with actually human behavior. And so to deal with that, we have come up with what we call representative concentration pathways, which are just really complicated ways of saying, basically, ideas or different versions of the future Earth, okay? And they've got this sort of complicated looking name, so RCP, which basically just stands for that radiative or representative concentration pathway, and then 2.6, 4.5, 6, or 8.5. Basically, what those numbers represent is how much of that extra radiative forcing are we going to see in 2100. So you can see the green line there represents RCP 2.6, which basically says that in 2100, what we're doing as humans to the system is going to be contributing 2.6 watts per meter squared to that warming of the climate system. And that's pretty similar, if we go back quite a long way, that's pretty similar to what we have today. We have about 2.5 watts per meter squared from these greenhouse gases. So whatever combination of world events and economic growth and population growth and energy sources, whatever that is, that allows us to create a radiative forcing of 2.6 watts per meter squared in 2100, that's what that pathway represents. And then if we go to the other end of the spectrum, our RCP 8, that's sort of our worst case scenario, RCP 8.5, where basically we're having an extra 8.5 watts per meter squared of energy added to the Earth system, okay? So our best case scenario is RCP 2.6. Some might say that's even too optimistic, really, given where we are right now. And then our worst case scenario is 8.5, okay? And so this is what those really are representing. So these are the different ideas for what the future might look like. And we're not saying that any one of those is right, but these are ideas that gives you a range of possibilities. So the population, you can see there, for our best case scenario, it sort of peaks in about 2050 or so, and then sort of stabilizes or even starts decreasing a bit. In our worst case scenario, it keeps going up to maybe, even up to maybe 12 billion. Okay, and then also what's shown here, in 2000, those different colors represent where we get our energy from. So the black is coal, the orange is oil, and then those others represent nuclear and then more renewable sources. And then you can see for the different RCP scenarios where our world's energy is coming from. And you can see that we still use a lot of coal in all of those. We use differing amounts of oil. And in all of them, we have to increase the amount of renewable energy sources we're using, even in order to get to our sort of best or worst case scenario, 8.5. The world there is still using maybe sort of 40, 50% renewable resources at that point for our best case scenario. And given what we have today, which is a tiny fraction, that's got quite a big change in terms of our energy sector. And what does that actually mean in terms of emissions of carbon? Because that's really what it comes down to. So the graph on the right here shows, again, our best case scenario, our green line, shows that the CO2 concentrations in our atmosphere are going to maybe peak in the mid-century and then sort of level off maybe at about 420 or so. We're about 400 today, to give you some idea of that likelihood. And that means that in terms of our emissions, we basically have to peak in terms of how much CO2 we're emitting in the next 10, 15 years. and then we need to start decreasing to the point where we actually don't emit carbon anymore from 2080 onwards. Okay, so now let's look at our worst case scenario. In our worst case scenario, our CO2 concentrations by 2100 are more like 900, 1,000 parts per million. The last time that we had CO2 levels that high was maybe 55 million years ago. So now we're talking really significant changes. And that's sort of, you can see that obviously to get to that high concentration in our atmosphere, we're just continuing to emit carbon dioxide by burning fossil fuels, and then eventually it does stabilize towards the end of the century. So those are just some possibilities. And I wanted to ask you, what do you think? And there is no right answer. I'm interested to know, which of those do you think might be what we follow? Okay, so you can see the emissions graph on the left there. Do you think we're best case? Do you think we're worst case? Do you think we're somewhere in the middle? Okay, a few more seconds for people digging frantically through their bags. Okay, well, let's take a look and see how optimistic our class is today on the last day of the quarter. So, not terribly, I think, is the answer. So we have, say, 26 people who are massively optimistic and think that our best case scenario is going to be our future. And then we have perhaps more people who think that the higher sort of CO2 outputs are more likely. So keep an eye on those, because I'm now going to show you a whole bunch of information about what our climate might become following those two different potential scenarios. Okay? So first of all, temperature. If we follow that 2.6 versus the 8.5, what does our temperature do by the end of the century? So our blue line there represents our best case scenario. Our pinkish reddish line represents the worst case scenario. And that range around that's the uncertainty. That's when we run 32 models, that's sort of the range of uncertainty that we see. When we run 39 models for that larger change, that's the range of uncertainty we see. But if we average those out, we see somewhere between a 1.5 degree and a 4 degree Celsius increase in temperature by the end of the century. Okay? And that's sort of from today. Okay? And that's pretty substantial. That's 2.5 to 6 degrees Fahrenheit. And I know to you guys that doesn't sound a lot, but I'm going to suggest to you that it is really very significant. Okay? Because this is what it is in context. This is a figure taken from one of those old reports again. But this shows the temperature record reconstructed from 1,000 years ago and then instrumental to today. And that's what those predictions basically do. So it may not seem a lot, but remember we had our little ice age where we had ice fairs on the Thames, and that was sort of here-ish. And we had a medieval warm sort of period, which is sort of here-ish. We are really, really drastically changing temperatures, really much faster than we can really find much evidence for in the geologic record. Even our sort of extreme cases don't change temperatures this fast. 1 degree Celsius means that we see much more drought and difficulty farming perhaps in the central US. Up to 4 degrees means that basically things like the Brazilian rainforest won't be able to cope anymore, and so we'd see very rapid disappearance of the rainforest, as well as things like perhaps much increased melting of permafrost and feedbacks there. So 4 degrees is substantial. We really don't want that to happen. And I wanted to recommend for people that are interested and are looking for Christmas presents, this is a really interesting book. It's not, again, easy bedtime reading, but it's a really fascinating book because it basically takes the world and it takes all the research that we've done and it says, well, what would the world look like if it's 1 degree warmer? What would it look like if it's 2 degrees warmer? What would it look like all the way up to maybe 5 or 6 degrees when we don't really have that much research because it's very difficult to find sort of analogies for this in our past. And if you can't be bothered reading the book, there's a 6-minute YouTube version, okay? So that's probably more likely for a lot of people, I understand. But it's a really interesting idea, and it really demonstrates just how much actually 2 or 3 or 4 degrees of warming actually is. And do you remember when we looked at what's happening today, we're saying that yes, we've seen warming already, and that warming isn't distributed evenly. And that's true also for changes that we're going to see in the future. So again, this is our best case scenario now on the left, our worst case scenario by 2100 on the right. And that's the change in temperature. The darker the color, the worse it is in terms of change of temperature. And you can say that even in our best case scenario, by 2100, we're still going to see potentially 1 to 2 degrees Celsius of warming where we are in California. If it's our worst case scenario, then we're seeing maybe sort of 4 or 5 degrees Celsius of warming. That's really enormous for California, but it's nothing compared to what the Arctic regions are experiencing, because just like the land warms more than the ocean, due to all of those feedback processes going on, such as albedo, methane release, things like that, the high Arctic is going to warm much, much more than the rest of the Earth. So our best case scenario, we're still seeing maybe 2, 3 degrees Celsius, which remember is as much as we saw in that last interglacial period when our sea level was 6 meters higher than today. In our worst case scenario, it's really unthinkable. We're seeing changes of 9 to 11 degrees Celsius. That's more or less taking the climate of somewhere down like around Mississippi and turning it into, or sort of turning Minnesota or something into that. So really substantial changes in climate due to this. We also see changes in precipitation. And again, we have a little less certainty here. So where you can see that there's sort of various different shading on the map, and that represents different uncertainties. But in general, the dry areas get drier, the wet areas get wetter. The more we change our climate, as in our worst case scenario, the more extreme those are. In general, what we expect to see is much more extremes between our dry areas and our wet areas, and also between our dry seasons and our wet seasons. Our hydrologic cycle is going to get accelerated. We're going to see some worse flooding events, worse droughts. Okay? So how about cryosphere, our ice? So obviously, as we increase temperature with the more extreme scenario, we're going to get more melting. But what do these changes look like? So here's just our sea ice extent, because that's such an easy one to imagine. And in the gray is sort of what our measurements are, and this is then what those models suggest. So our blue, again, is our best case scenario. We still see a decrease, but actually, if we manage to follow that scenario, we still have a certain amount of sea ice present in the summer in the Arctic Ocean. But if we follow much more of those higher emission scenarios, then really our sea ice does more or less disappear in the summer, and potentially by 2070, 2080, it's more or less gone. Okay, so this is our sort of best case scenario with plenty of sea ice, that white area still present by 2100, and what the Earth might look like in the summer of 2100 if we follow these much higher emission scenarios or the representative pathways. Sea level. Sea level is an interesting one, and I had to change my slides quite a lot because even from the last report, the estimates for how much sea level rise will occur have gone up. Okay? This still seems to be somewhat conservative. So these are our projections, our best case scenario in blue. We get maybe 45 centimeters of sea level rise. No, sorry, yeah, about 40 maybe. In our worst case scenario, we maybe get more like 75 centimeters. So I'm 1.5 meters tall, pretty short. And so 75 centimeters is like that. It's not trivial. It really isn't trivial. We've already seen sort of 10, 15 centimeters. That's already causing us trouble. And I think there's a really cool little link here that I've put, which allows you to explore a little bit about what that means in terms of places. So here's a little map, and you can zoom in, for example, on Orange County. Okay? And what you can do is you can change, so this is how much area of that would be flooded with 1 foot of sea level rise, with 2 feet, with 3 feet, with 4 feet, with 5 feet, with 6 feet. So you can find out where your sort of house is and look at sort of how far above sea level it is. Okay? So here's a little geography question for you, because I know how much you all love geography, and I know you've been missing maps and everything else. So what is the US state with the lowest elevation above sea level? If you're international, you can consult your neighbors if you want. Okay, a couple more seconds. Sorry? Oh, sorry, you can tell it's the last lecture of the class. A, B, C, D is normal. Sorry about that. You can't get 2 answers at once. Okay. Oh my goodness. Not enough sleep in the last few days. Okay, so let's take a look. So, you fell for my question. Florida actually isn't the lowest state on average. It's actually Delaware. So, do you happen to know, all of you American people, especially you history majors, which was the first state to join the Union? Delaware, absolutely. And I heard a talk by someone who was very pessimistic about sea level, and he was basically going, first in, first out, okay? Because Delaware is very, very vulnerable to sea level rise, but as is Florida. And I had a couple of maps to show you. So this is sort of a pretty sort of bad resolution map of the US. And in red there are those areas that are vulnerable or would be flooded by a 1 meter sea level rise. So that's about 3 feet. So it's a little bit more than that estimate for the end of the century, but not that much more. So you can see how much of Florida disappears. And in particular, Miami is not looking good. They basically got a whole bunch of engineers from the Netherlands, and the Netherlands is a really low-lying country that has this very extensive network of protection against the sea level. And they got them over here and they said, tell us how we can protect Miami. And they basically said, you can't. It's really in trouble, and really by the end of the century, if we see those upper ends of sea level rise, it could be in real trouble. It's just got such an enormous coastline. It's on this really porous rock that it could be in quite some trouble, okay? And it's not just the US. And we have money, we can relocate, but actually some countries, such as Tuvalu, this is what their country looks like. They don't have anywhere else to go. And this is, I think, one of the more sobering thoughts about this, which is that 1 meter of sea level rise could actually wipe out certain countries. And I think that's sort of somewhat horrifying, that sort of our actions in terms of how much CO2 we produce, especially in the coming sort of 20, 30, 40 years, will control whether this country can exist or not, will control whether those people that have lived there for hundreds of years, that it's their home, are going to be able to stay there. So this is a really serious issue, and so obviously it's a very politically charged one as well. Often these nations in particular are really leaders in terms of trying to get people to address climate change. There's no real way around it. Other places, such as Bangladesh, are also extremely vulnerable. Basically about 20% of Bangladesh would be flooded by a 1 meter sea level rise, and it has a very, very dense population. That's 14.8 million people. Probably 100 million people worldwide live within 1 meter of sea level. And so this sort of becomes a very contentious issue, and these countries really are going to struggle with trying to protect against sea level rise. It's something that Newport Beach can deal with. They're planning for it, they're dealing with it. It's something that this sort of country with enormous coastlines will struggle. Okay. So let's look at ocean pH. And I want you to note in particular, compared to those other graphs I've shown you, the uncertainty associated with pH of the ocean is much, much less. We can tell you really very precisely what the ocean pH will be given a certain CO2 concentration in the atmosphere. The temperature and climate is a bit more difficult to get at. And so you can see that in our best case scenario, we sort of level out pretty soon. We see a change of maybe 0.1 pH units, which remember, because it's a log scale, is still something significant like 26% something. If we go with our worst case scenario, we're seeing a change of more like 0.4 pH units. And that is really, really, really troubling. At that point, our corals are really going to struggle to grow at all. We'd also see very, very strong changes in terms of our mollusks, like sort of seashells. We're already today in parts of Washington state, which is very dependent on fisheries and their oyster farming in particular, they already have to address the water chemistry where they're growing, and actually they grow their sort of new sort of baby oysters, I don't know what you call a baby oysters in farms, and then transplant them out into the wild, into the more natural environment, because otherwise they were getting failures each year because the water was becoming too acidic for them to grow in. So this is something that it doesn't get mentioned at all, but we can actually project with much more certainty, and there are really very dramatic consequences associated with this. So it's a big change. So there's a little summary of those changes that we can expect. Best case and worst case scenarios. So carbon dioxide, somewhere between 400 and 950. A warming of 1.5 to 4 degrees. Precipitation will be sort of dry areas drier, wet areas wetter. The cryosphere will continue to melt. Sea level will continue to rise. So you can see I've put my 0.45 to 0.75 meters there. But we do have a certain amount of uncertainty due to those big ice sheets, things like Greenland and Antarctica. And we don't fully understand how quickly they're going to respond. There may be additional sea level rise due to those. Ocean pH, a decrease of 0.1 to 0.4. And others are things like changes in the timing of the seasons, which messes up the biosphere. Also increases in occurrences of extreme events like big hurricanes, typhoons. So maybe not the number, but certainly the intensity of those is going to increase. And also things like droughts and flood events, those will also start having an effect. Okay, so that's what the climate is, but how is that actually going to affect us? How is that going to affect things like our water supply? So this basically says for 0, 1, 2, 3, 4, 5 degrees Celsius increase in temperature, what would happen to things like our water availability and so on our ecosystems. So you can see even with a 2-degree increase in our temperatures, maybe 30% of species would be at risk of extinction. 30%, a third of life on Earth nearly. And then as we increase that, it just gets worse and worse. Things like the terrestrial biosphere, or corals. Corals will really die out sort of more or less from 3 degrees onwards. And so that's a problem. With our food, we definitely, with the bigger temperature changes, we'll see a real shift in where we're able to grow certain crops. And that's going to have a very big effect on, say, farmers and farming areas. Things like coastlines will get much more flooding as we increase temperatures more and more because of that thermal expansion. Coastlines and coastal wetlands will be lost. Health, we're going to see changes in disease vectors. We're already seeing that in parts of Europe where sort of mosquitoes that previously it was too cold for them to sort of survive. We're seeing that shift into Europe. We're also seeing shifts, say, in parts of Africa. Certain cities were built above a certain line where mosquitoes sort of wouldn't go above because it was too cold, and they're definitely seeing changes as well. So things like that are also going to affect human populations. So what are our uncertainties? So I've told you that's really what we're expecting, and we have a certain amount of confidence in that. But there are always uncertainties in our models, and I don't want to pretend to you that we know absolutely everything precisely down to the 0.1 degree. The uncertainties in our climate models are things to do with the response of clouds. And we have a really cool new faculty member in our department who is trying to do that much better in climate models and build in clouds. Things like the potential for sudden shifts in our climate that we may not be accurately able to model yet. Things like changes in the biosphere, sea ice changes, which seem to be happening more quickly than we expect them to be happening so far. Ocean circulation, maybe. And also ice sheets. Ice sheets are really a big sort of black box still in a lot of ways. We don't necessarily have that much confidence that we know how they're going to respond and how much, therefore, they might affect sea level rise. So there are these uncertainties still, and they're really interesting aspects of the climate system to look at and to try and research, and that's where a lot of the people in our department are working. So I've told you all of those things and thoroughly depressed all of you, no doubt. But what can be done? There is plenty of stuff that can be done. First of all, and the most obvious thing is, if we're going to try and follow our best case scenario, we need to be cutting out our carbon emissions. We need to be peaking in the next 20 years and dropping, and then cutting it out more or less completely from 2080. That's going to involve dramatic changes in our transport sector, in our energy sector, in our food sector, all of these things. And so things like the Kyoto Protocol were brought in the 90s, I think, the 1990s, to try and encourage countries around the world to come together and commit to reducing carbon emissions. That's really the fundamental thing we need to do. And in green are all the ones that have signed and ratified. In red are the ones that actually withdrew, so Canada decided to withdraw. In brown is the country, there's only one of them, that signed it but refused to ratify it. Okay? Not good. Independently, some states, some cities have actually agreed and ratified the Kyoto Protocol within the US, but the US as a whole has not agreed to do that. And really, therefore, it stands very much alone. So, let's have a look again at what we might need to do to follow our best case scenario, because I think we would all agree that we quite like to follow our best case scenario wherever possible. So it looks like if we look at our energy distribution, for example, for our RCP 2.6, we can increase our coal emissions a certain amount, but we need to cut down on oil. We need to massively expand things like our bioenergy and build up hydro and solar around the world, and also build more nuclear, which is never a popular option with a lot of people. Had an interesting debate with someone recently about that, but it's something. We also need to keep track of our population and not let it expand too much. That would help us follow this lower RCP. And just as a reminder, in order to follow that scenario, that's what our emissions need to be. And this isn't necessarily something that, therefore, we can think about in 20 years' time when we're over this economic crisis and over the next economic crisis or anything else. We need to be thinking about switching our economy now, because it's going to take time, it's going to take significant investment, it's going to take significant innovation in a lot of ways. Okay. But the good news is that we do have a lot of this technology. It's expensive, it's more difficult, but excuse me, I can hear you from the front, so people around you must be really angry. Okay, so the first thing we can do is stop deforesting areas and start to reforest. Regrowing forests would definitely be a good way of sort of stopping some of that CO2 rise. Switch to alternative energy sources. We have a lot of alternative energy sources. Yes, they're more expensive, but they are good alternatives. And now it's more of an engineering challenge. How do we, say, take wind power from where it's most sort of generated and transport it to cities? And how do we cope with the fact that wind will change on an hourly and daily basis compared to, say, our nice steady output of coal and oil power stations? Increased energy efficiency, this would be a huge one, and we can all do this, because I wander around campus and at night you can see the lights on everywhere and everyone's screens are always on. Things like fuel economy in cars, we're getting much better at that, but still there's improvements that can be made. Changes to farming methods could be a big one, things like the fertilizing. Carbon sequestration. So that's where we try and take carbon out of the atmosphere in some way. So people have tried liquefying it and pumping it down back through oil wells and try and locking it into the earth. We're not still convinced how much of it actually stays down there. And again, it's still a really energy demanding process. And then geoengineering solutions. And I like these because there are some crazy ideas out there, okay? So from giant space mirrors to these boats that float along and spray out sulfur aerosols from the ocean. So these are some of our engineering solutions that have been proposed, seriously proposed by some people. And so in blue, those little blue dots represent how effective they would be. So our space mirrors would be really effective at changing the Earth's temperature, okay? But it would be really expensive. And it's also technology that we just don't have yet. We're sort of really centuries away from having deployable space mirrors, okay? Foresting areas. Foresting, if you look up there, it would actually be really pretty effective, okay? It would be relatively cheap, okay? It's relatively ready. It would be sort of available within decades. We could lock away quite a lot of carbon on that sort of time scale. But you can see that each of these has sort of flaws associated with it, okay? And one of the biggest ones is that a lot of those don't address the problem of ocean acidification, okay? So take a look at this and see which do you think of those solutions there would actually solve the problem of ocean acidification, okay? So have a think, talk to your neighbors for a second, and then I'll ask the question. So remember that ocean acidification is caused by high CO2 levels. Which of these would fix that? Okay, a few more seconds for the last few votes. Okay, let's take a look and see if we agree. Good, we do. Okay, so yes, so foresting would be a really good way of fixing both problems. It would fix the increasing temperatures due to those increased greenhouse gases, but it would also fix the ocean acidification. There's things like space mirrors, things like cloud seeding, things like spraying aerosols and sulfates into the atmosphere. They would affect our albedo, but they wouldn't ultimately address the problem of building up CO2 in our atmosphere, and so they wouldn't address the problem that we're going to experience of our acidifying oceans. And so that's the case with a lot of these things. And these are nice ideas, and it's definitely a good idea to think about outside the box a little bit on this one. But a lot of these things won't address the fundamental reason, and that's why I show you these, because they're interesting ideas, but in terms of actually helping us in the next 20, 30 years try and avoid more of these really dramatic changes by the end of the century, we're really going to need to do things like alternative energy sources. There's no way around that, really. We're going to need to think about things like increased efficiency and carbon sequestration, okay? So those are nice ideas, though. So, this is a whole list of questions that I don't want to necessarily read through now, but I want you to think about, okay? I want you to think about things like the fact that the human race is not going to go extinct, okay? The world will not end, even if all of Antarctica, even if Greenland all melts. We've had times in the past when it's been just that hot. We've had sea level hundreds of meters higher than today. The question is, or the problem is that we definitely wouldn't be able to support as many of us. And it would be a very, very different world. It wouldn't be as sort of friendly a world to us. And so what sort of world do we want to live in? It sort of comes down to that. In the US, we won't necessarily experience the worst changes, and we also won't necessarily experience hardship because we can adapt to those changes. But how much responsibility should we feel for the rest of the world for actions that have caused them that hardship? So things like how much responsibility should the developed world take, and how much CO2 should we cut? And at the end of the day, that often comes down to a more personal decision. How much are you willing to change your lifestyle in order to try and avoid some of these big changes? How much of a role should government have? Some of these are really important questions to, I think about and ask. Okay? And it's also worth making the point that I've shown you up to 2100, but the world is still going to exist after 2100, and I hope that as a human civilization, as people, we've evolved to the point where we're capable of thinking beyond the next year and beyond the next 100 years, and actually think of sort of human civilization beyond that. I went to a university which was 1,000 years old. I hope it's still there in 1,000 years' time. I hope that this is still here in 1,000 years' time. So the next 100 years is a really small time in terms of human civilization. And so this is sort of an interesting, I think, thought experiment showing what might happen, what those RCPs might look like beyond 2100. And things like our temperature rise will continue to increase because we're still going to have that CO2 in our atmosphere after 2100. We're not going to just cut off then. So we're committing that next generation after 2100 to even further changes. So this is something that we need to think about. Okay, so I have 3 last slides, so please don't pack up until then, because we'll be done a little bit early. This is how I end all my classes, okay? Oh, wrong way. So for those of you that I've told this already, don't give the game away. Does anyone know what this is a photo of? It is a photo of Earth. Can you see it? It's up there. Okay, this is the furthest photo that was ever been taken. It was taken by one of the probes that they sent out very early on in the 60s and 70s. And I'm not going to read it now, but I've included a piece of writing that was done by Carl Sagan, who was really a leading scientist of our generation and who had very profound sort of ideas about these things. But he basically, to summarize it very ineffectively, he said, that's us. Everything you've learned about, every person that has ever lived, everything you've ever sort of known about has happened on that dot. And that's it. There's nowhere else that we can go right now. And that's worth thinking about when we talk about things like climate change, sustainability, and resources. This is it. There's nowhere else for us. And if you ever hear of this, of the astronauts that go out to space and get this have this revelation that we are this little island floating in space, and we are sort of very isolated and alone in some ways, okay? So do read that. I think it is sort of very profound. And so lastly, I want to thank you all for your hard work. I know it's been a long quarter, but hopefully, apart from your grade, I hope you take something away about the world in general, and also thanks to the TAs. Okay, thanks guys.